things so far? No questions. So one thing I want to say is that the 4B is going to be like a leap, right? So it might so far the assignments might have been tedious, but fairly easy. 4B might seem a little bit more difficult because you have to come up with your own lemmas. It's sort of doing very familiar things, right? It will ask you to prove things about binary search trees, but the deletion proof will be the theorem and the proof will be a little bit tricky. Let me put it out there, right? Okay, so we might even come back and go through the solutions after the um, deadline is done, if we want, right? So make sure you start early is the reason why I'm saying this. I found it to be like, okay, this is slowly building up and suddenly there is a jump, right? So I think this jump is I want to make you aware that there is going to be this small jump. Try it. I also had other students in the last year who said this was easy for them. They were able to complete it very quickly. Um, but again, these sort of proofs are the one thing that you sort of will find is that it is not the amount of time that you put in, it's sort of the intuition that you develop for these proofs and how you structure the proofs that help you a lot. Um, so so start early so that you're not left with less time to actually put in the required amount of effort. Anyway, so with that, let's just finish off this interpreters lecture. So the last thing that I wanted to actually talk to you is one optimization, which so we are looking at this just to remind you, right? We were looking at this imperative language, which had constants, variables, expression language that we had earlier, but also a small command language, which had a skip, assignment, sequencing, and then repeat. This repeat is special because it's a repeat. It's not a while loop. It repeats a fixed number of times. We described it this way so that Coq will allow us to write programs in this language. Otherwise, if you had a full generalized while, Coq cannot prove the termination of an interpreter for this language. But here in this specific case, we can prove the termination. That is why it's called repeat and not a full while. So we saw the semantics of this language, right? How do you describe the semantics? We are just going to see one optimization, right? This optimization is sort of very common in compilers that do that process a lot of mathematical kernels, right? So if you happen to do any sort of machine learning, any sort of GPU work, this sort of loop unrolling is a very common optimization, which basically says I have a very short loop. I want to just unroll the loop, and the idea is that when you unroll the loop, you expose more optimization opportunities for the subsequent phases of the compiler, because the loop, you no longer have this loop, you just have straight line code. And when compilers see straight line code, they can do far more optimizations. And I mean, there are various ways of doing this. You don't have to unroll all of the loops. You can sort of tile the loops as well. You can say, I know this is a tight loop. I will just unroll it. If I know that the loop has 1000 iterations, I will unroll it such that I have 5 iterations expanded, and I do 100 iterations of this new expanded one. All of this sort of gives you a lot of opportunities for optimizations in the later phases. But what we are going to see here is something very particular. So we are going to say, oh, I will implement this loop unrolling. I want to prove that the program semantics does not change if I unroll my loop, right? That's the thing that we are going to show. So because we are unrolling loops, I'm going to introduce a new syntax, right? Just to describe what unrolling means. So, so here is the first thing, right? I take a command, and if I sort of have a superscript which is 0, that basically says I'm going to unroll this command 0 times. When you unroll something a 0 time, it means that you're not executing that command. So we just say that the meaning of that is skip. If you want to unroll a command n+1 times, right? So repeat a command n+1 times. It is the same as syntactically transforming it, right? So I'm sort of saying command once semicolon n times of the same command. So what you're doing is you're doing syntactic transformation, right? You're this optimization. You can sort of think about taking the source language, right? And if the repeat is going to be constant, it is going to give you a program in the same language where the loops have been unrolled. The loops with constant iterations have been unrolled, right? What does that mean? So if we understand this one, we can actually see how this unrolling is described. The unrolling is itself described as a recursive function. If you unroll a skip, you just get a skip. If you unroll an assignment, there is nothing to do. You just get the same. If you unroll a sequencing, you unroll the first command, you also unroll the second command, right? And here is the important step, right? If you unroll this repeat, where the number of repetitions is a constant, you actually know how many times this loop is going to run, then you actually call this particular definition, right? You unroll the body, which is C, but you also say, okay, syntactically transform this repeat into a bunch of semicolons, right? So semicolon, 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 and so on. But if it's an arbitrary expression, we don't know what the expression does. We cannot unroll it because we have an assignment statement as well, right? We cannot do this statically. We actually have to execute the program. So here we don't do anything interesting. We just say we'll keep the repeat as it is. We'll just unroll the body of this command. So the only interesting thing is this particular command. This command here, where you are repeating something n number of times where n is a constant. Okay. Questions on this? Any questions on this one? Okay, so that's fine. So if there are no questions, so here is what we are going to do, right? What do we want to prove about this unroll program? If you unroll the program and then you execute the program under some valuation, it's the same as executing the original program under the same valuation, right? So that's really the intuitive definition of what unrolling means, and that's what we are going to prove. So here is the same thing in POC now. Okay, so let me make it a little bit bigger. Zoom in and then zoom in again. Okay, so what the sequence self says is that it's this function here, right? This function is doing the same thing as what this particular thing is doing, right? If it is 0, it is skip. If it is n+1, it is going to introduce. It is going to transform it into a bunch of sequence of commands, right? So if I take a command and then I want to say sequence it n times, if n is 0, then you just get skip, which is the same as this one. If it is n+1, then you introduce sequence. So the sequence is, again, recall that sequence is part of the language that we've defined, right? Where is sequence? If we scroll all the way up, you will see that, yeah, sequence is part of the language. Sequence is, you just read sequence as semicolon, right? So all we are doing is that if you want to sequence this command n times, it is the same as sequencing it once and then doing it n-1 times, or you can read it as n+1 times. You just call the recursive function again with n times. So this is describing this part of the definition here. Okay, that's sequence self. And what is this unroll function? This unroll function is what is described here. Everything is the same. The crucial case is this one, right? The crucial case is I am doing the command that I observe is repeat of constant of n. N is a constant. If it is a constant, it is the same as expanding this loop n times. So you unroll the body, but also just use semicolon to expand it n times, right? and rest of the commands are the same. You just call unroll at the appropriate sub commands, right? So that's going to be the same. So here is an example, right? So I have a command here which says repeat 5 times the skip command. And this is sort of just to show how it appears, right? So this is the original program. If I unroll it, what I get back is what you would expect, right? Skip 5 times, 1, 2, 3, 4, 5. The last skip is because we have a 1 for 0 as well. So 0th skip is just adding one more skip here. Okay, so that's the expectation. So if you give a program, initial program, if it has a repeat of a constant n, it unrolls it this way. What we're going to show is that the semantics of any program, right? Here is one program. The semantics of any program, if you unroll it, is going to be the same. Okay, so that's what we're going to do. In order to do that, right? So here is what you will often find, right? Often we don't end up writing intelligent lemmas directly. You sort of go with the main theorem, and then you come back and say, okay, I need this lemma to be proved, so I'm going to prove this lemma. So here is a lemma that comes in very, very handy in order to prove this. So what does this lemma actually say? It just says that self-composition is extensional. What this means is we can just read it, right? So it says for all types A, let me consider two functions f and g, which are functions from A to A, right? They are just functions from A to A. And let me also consider some natural number n, some n, right? And some input x. And what do I know about this function? I know that for all y's, right? For all y, f of y is the same as g of y. I mean, if you sort of think about it, if for all y, if f of y is the same as g of y, f and g are the same functions because functions work that way, right? If for all inputs they give the same output, then they are the same. So if we have that property, which essentially asserts that they are the same function, then self-composing that function, right? If you compose those functions n times, what is self-composition? It is applying the function on it again and again for n times, right? It is the same. It is going to give you the same result. So if you self-compose f n times with the original input n x, then it is the same as self-composing g n times with x. Again, what is self-compose? Self-compose is something that we defined earlier in order to give semantics for repeat. Self-compose is going to be here, right? So it is repeatedly applying the same function on itself n times. This is very obvious, right? But this fact comes in handy. All we are saying is that f and g are essentially the same function. If they are the same function, then self-composing those functions n times over itself gives you the same result, right? So this is some obvious fact that we are proving, right? Again, in order to prove this theorem, we are going to induct on n because n starts at 0. We can prove it by induction on n. So we induct on n, simplify and try equality. This makes the base case go away, right? You can step through it and in your own time and see how it works out. So now we have to prove that this inductive case, right? We have the induction hypothesis here, right? We also have this H as a hypothesis. This comes from the statement here, right? This is part of the hypothesis. So earlier we used to do intros, right? And that is sort of directly done for us by this induct rule. It is playing double duty, right? But you can step through this and see how this H comes through. But this H is exactly the same as this thing on the left hand side of the arrow. It's the antecedent for this consequent here. That's the precondition, right? Assuming this holds, we are going to say that we are going to show that this holds. So what can we show, right? We know this is the same function. So we know for all f of y, it's the same as g of y. So the thing that we are going to do is to rewrite this f of x with GFY. So if we rewrite it, what has happened is we had f of x, right? We had f of x here. By using h, I'm going to rewrite it as g of x. Why am I doing this? If you look at the induction hypothesis, right? It says that for all x, right? And assuming that this property holds, which is f and g actually act as functions, self-composition just works out, right? So if you look at the terms here, I have f self-compose fn, self-compose gn, right? I have self-compose fn, self-compose gn, but this x argument here is a for all quantified argument, right? So that can be substituted with any term at all, right? So I have an x here and x here, and the observation is that this is a for all quantified variable. So I can actually substitute that for g of x, right? It doesn't matter what that x is; it's the same term, so they are the same. So now you can apply this induction hypothesis, right? You can apply this induction hypothesis thanks to the fact that this x is universally quantified. And what does application of this induction hypothesis do? As we've seen previously, we are going to do backwards reasoning, right? Assuming this is going to match with this, we need to show that this property holds, right? If you apply the induction hypothesis, our obligation is to show that this precondition holds, and this precondition holds because it's part of the hypothesis here, right? So for all y a, f of I equals g of I, which is what the hypothesis is. So trivially, this is true, and this goes through. Actually, we've not proved something very difficult, right? We proved something that is very obvious, but this proof is important for us. Okay, so that's the proof of self-composition is extensional. And the most important lemma for this one, right? What we are actually doing here is, if you look at this one, right? We have repeat const n here, and we are saying we can replace that with a sequence self, right? We can use sequence self here. But if you look at the original execution, the interpreter that we have defined for this one, the repeat here is going to be converted to a self-compose, right? So the self-sequence, we have to somehow relate the fact that the self-sequencing, which is like taking a command and sequencing it with semicolon n times, is related to this composition, which is applying the same command n times. And that is precisely what is being captured in this lemma. So what we are saying in this lemma is that consider for all commands, for all natural numbers, any natural number n, for all values, if you execute the program where this command is repeated n times. So the way to read this is that it's C semicolon, C semicolon, C semicolon n times, right? If you execute that program under the valuation V, that's the same as executing the original command, right? By self-composing it, right? So you execute the original command n times with this original V. So you execute once, you will send a V inside, it'll get a V outside, right? Because our execution itself is a value transformer. You take a valuation in, it gets a valuation out. If you keep doing that n times, we are saying that it will give the same semantics, right? This is expected, right? Because if you repeat the sequencing n times, it's sort of the same as saying, oh, this valuation is transformed once, it is transformed again, it is transformed again, and so on. We are sort of capturing it the same fact in a different way. So this is essentially transforming a program. Here we are actually talking about the semantics of self-composition. So the crucial lemma is to relate the self-sequencing with self-composition, which is what we've done here. Actually, once you write the lemma, the proof itself is very, very straightforward. In fact, it just goes just with induction, simplify, and equality. Of course, it goes through each of the cases. You can expand it and step through, but it's so trivial that it goes through. Okay, so what we've now done is that we've sort of related how the self-composition, which is applying a function to itself, is related to expanding, sequencing a particular command n times, right? We've done that. We've done the hard bits of what is required for the proof to go through. We need to now prove the main theorem, which is that if you execute the unrolled program under this valuation v, then it is the same as executing the original program. I mean, this is what we want to do, right? I'm implementing a compiler optimization. It better be the case that the compiler optimization does not change the semantics, which is what we are proving here, right? And of course, we don't have an n or something here, so we are actually inducting on the structure of C. So we are going to case analyze and also apply the induction hypothesis. So we are inducting on C. The simple cases, we are going to just make it go with try equality, right? And after this, right, it is going to be very, very mechanical. So we have a match with, and then we have two cases. As we've seen earlier, when we have match with, we have to use case analysis. And the way we do it is we do case analysis, and then we simplify and try equality. So one of the cases goes through, right? And we have 5 other cases come through, right? And in each of the cases, what we are going to do is to use the fact that we've learned, right? Which is that this, so this case is essentially, what is this case? This is saying if you have self-sequencing of unroll of C, which is self-sequencing is that using semicolons, right? That is going to relate to self-composition. And we have the induction hypothesis that shows that if you unroll C and execute it, it's the same as executing C directly. So we appeal to our lemma that we just proved, right? We appeal to that lemma. Now we have a structure which is going to be like, okay, I have self-composition here, right? But the thing here is that the induction hypothesis does not refer to self-composition. The induction hypothesis actually talks only about the body, right? And this self-composition, we have to say something about self-composition. That is precisely what we proved in the previous lemma, which is that if you give me two functions which are essentially the same, the self-composition is going to be the same. We proved it in the forward direction. We are going to apply the backwards reasoning, right? We have self-composition here. So I'm going to apply this lemma and show that these functions are going to be the same, right? So when I apply self-composition here, the obligation that I will get is precisely this one, right? Which is to show that for all y valuation, executing the unrolled function is the same as executing the original function. This can be proved thanks to the induction hypothesis that we have here, right? So we've used two lemmas and we've also used the induction hypothesis. And that trivially goes through because they are the same. And the rest of the cases, it's all about removing the self-composition, right? We know how to remove self-composition thanks to self-composition is extensional lemma. And once you do that, the induction hypothesis makes it go through. So the rest of the cases is exactly the same. So you keep doing that, then we've proved that executing the original program gives you the same semantics as executing the unrolled program. So of course, proving real compilers correct is a great challenge, right? And in fact, one of the key achievements of using Coq is we now have a compiler called ComCert. Okay, ComCert is a compiler for a very large subset of C. So it's not a very small subset. It includes a very large portion of C language, right? And the compiler itself is actually written in Coq. So the compiler is written in Coq for the exact reason that we've seen here in the simple example, which is that you start from the C language and our target is say x86 assembly instruction, right? And what the compiler actually does is compiler construction you've studied in the previous lecture for the undergrads, and for the graduate students you've seen that in your previous undergraduate courses. We describe it as multiple phases, right? And what this ComCert compiler does is that for each of the phase that you have, it sort of tries to prove the same thing that we've tried to prove here. which is that if you take the original program and you execute it under some semantics and you apply the compiler optimization and you execute it, you end up with the same semantics. So at each of the phases, it proves that the program semantics that you expect in the source language is the same as what you have in the second in the target language, right? And if you sort of apply it for the entire compiler, you get the compiler full compiler correctness. And this is like a significant achievement in verified compiler development in the last 20 years. And why is this significant? This is significant because most of our software, right? Even though I teach OCaml and we see Coq and everything, industrial software is still written in C, right? When we write C, C is one of the strangest languages to succeed, right? It is very, very powerful because it is so low level, but it is also very strange because there are so many corner cases in C. But software such as like Airbus fly-by-wire systems, right? And even I don't know whether you came across this Mars Perseverance lander landed last week, right, in Mars, and they have this very small helicopter which they are going to fly in Mars. So this will be the first time we are going to fly anything, right? Powered flight in a different planet. And this particular software is actually written in C, right? Because we have so much expertise built in C. But how do you know that the software that you've written is actually going to be the same thing that you've get in the assembly, right? We don't have confidence today. So if you write GCC or LLVM or use any of these compilers, of course, as compiler engineers, we are not being malicious. We want to make sure that our software is correct. But as humans, we make errors, right? But this ComSert project is so beautiful that if you have a semantics for the source language, then you can be sure that the compiler will preserve the semantics in the target language. I recommend you to have a look at this compiler called ComSert. It compiles a significant subset of C. I mean, the second question is how efficient is it? It comes within 15% of GCC, right? This is data from few years ago. It might have diverged or converged, but really performance is not the key aspect these days, right? We have so many security holes and these things that we really care about the correctness. And ComSert is sort of following the same principles. If we have time, we will sort of look at compiler correctness and how to prove realistic compilers correct in this course based on the time, right? So we will see whether we have enough time to actually do this exercise in a more interesting language. This is a very small language, but we'll do it in a more interesting language. It's sort of very exciting, right? So we write all these compiler optimization phases. How do we know that they are correct? And this is one way to do. This is one way to do it. We also have lots and lots of challenges in proving real compilers right, and we will see some of that in the possibly if we have time in this course. So, any questions on this so far? No questions. Okay, so what I'm going to do is to try something different from the last time that I taught this course. So what we are going to do is to actually switch to F star at this point. So this is a good point to switch to the F star language because we've seen how to do small programs and prove it and so on. We've not actually got into the depths of how to prove more complex programs, right? Which means how do you describe things like concurrent systems and infinite systems? For example, the language that we have here, right? It is a terminating language, and the way we proved it is by writing an interpreter. But you cannot write an interpreter for a non-terminating language. If you really wanted to prove C, you cannot write semantics in the same way because um, the interpreter that you will write for the C language will have to handle infinite programs, and that won't be allowed here. There is a different way to do this, and this forms the meat of the course here. And we will come across techniques for reasoning about mutations and so on. But what I want to do is to actually do that later. I actually want to show you another way of building verified software, which is through FStar, right? FStar is an exciting language. We'll sort of motivate FStar mostly in this particular lecture, and then we will see how far we get with FStar in this week. So I think it's a different thing, but you'll sort of you'll see a lot of commonality between how we've done things in FStar and how we've done things in Coq. So, okay, let me load that up. This says Spring 2020, but it should be Spring 2021. Okay, so let me set this up. I also want one other thing for this. So for FStar, there is a very nice UI. It's Emacs, but you don't need to know much of Emacs for doing this. There is also an online version of writing FStar in an online editor, but I don't recommend that much that editor. So FStar has VS Code plugins, Emacs plugins, Vim plugins, Spacemacs plugins. I use Spacemacs, which is an editor which sort of gives you both the experience of Emacs and Vim. If you are going to be a serious programmer, I recommend learning one of these tools, right? I believe that VS Code is the hip thing today, and VS Code plugin is available for FStar. I have some information linked from the website for installing FStar and installing the Spacemacs UI, which is what I'm going to use. But for VS Code, if there is any trouble, I think one of our TAs will help you with that. I recommend. I don't particularly mind which one you use. So let me start with this one. Okay. So this is how Spacemacs will look like. So it's going to be a little bit small, but it's going to blow up a little bit later. Okay. So Spacemacs is a combination of Emacs and Vim. I'll make it bigger. So what I'm going to do is to switch between, for the first few classes, I'll sort of have some slides, which I will show, and then switch between that and code. And it'll be an interesting experience looking at both of those side by side. FStar is actually a wonderful language. And we have been using FStar as a research vehicle for some of our research. Vimala is also hacking on it. Shira is hacking on it. The two TAs are hacking on it. So they know a lot about FStar as well. I believe that FStar and similar languages are going to be the future, right? Rust is sort of heading in the direction. But as you go along in the next 5-10 years, you will see more and more of these sort of languages, ideas being incorporated into the real world languages. So sort of treat FStar as the early prototypes, right? If you sort of imagine, what do you call it? Say when Tesla introduced their first car, right? They introduced the Tesla Roadster. Roadster was a sports car, right? It was not targeted at a casual buyer, but it does a lot of good things, but it also has lots of faults, right? So early movers sort of bought all the Roadsters, and that gave them enough experience so that now they have Model S, right, and Model E. Model E is the cheapest version, and they're going to introduce the cheap versions in India as well, right? So that's the same way language also evolves, right? We will have vehicles for really advanced ideas, and then what we will do is we'll sort of then see these ideas percolate into real world languages. So Deepali had a question. I missed the question. So what was the question? Is there any drawback of using Coq so FStar is used? Actually, we will see some of that in this lecture. That's the point of this lecture. You will hear about it more as we go through. So what we're going to do is to sort of look at how to do basic functional programming in FStar. So FStar language itself, right? It's OCaml. Basically, the heart of FStar is OCaml, and then they've added a very nice verification system on top. So you can do all the sort of really rich program proofs that we want to do directly in the language that we are writing programs in. It is different from Coq. So why is it different and how is it different? That's the point here. So if you look at the state of proof assistance today, you have basically two camps, right? On the left-hand side, you have interactive proof assistance. We've seen Coq, right? And there is also this very popular proof assistant called Agda. There is a really interesting proof assistant called Lean, which is from Microsoft Research. FStar is also from Microsoft Research. So Lean has this extremely ambitious goal of formalizing mathematics, right? So most of the mathematics that we do today are on pen and paper, and Lean has this advanced foundational system which allows you to formalize all of mathematics, right? This is like a very ambitious goal, and I'm sort of like a keen outsider. I know nothing about Lean, but there is this project called Xena, which is going to formalize all of mathematics in Lean, right? And there is also another proof assistant called Isabelle, which comes from ML tradition. Actually, this term called ML, right? ML stands for meta language, and the reason why this ML language was invented was for doing program proofs, right? And they wanted a language for manipulating terms, just like we have Galena for writing functional programs in Coq. They wanted a language for writing proofs, and the proof language is called a meta language, right? And short form of meta language is ML. Like even before people wanted to write programs in OKML or standard ML or Haskell or even Scala, right, which is also comes from the same tradition, ML was used for proof language, right? And that is where the tradition comes from. And Isabelle is sort of one of the early movers. And Isabelle Hall is from where standard ML came from, and that is where OKML came from. That is where sort of Haskell and Scala and other languages came from. So Isabelle has a very interesting tradition as well. So on the left hand side, you have interactive proof assistance. Okay, but on the right hand side, we have what are known as semi-automated verifiers of imperative programs. So one of the other things that has happened in the last 10, maybe 15 years now is that there have been extremely great tools and engineering that has been done in automated program verification, right? So essentially, these are built from SAT solvers. So I give a small question which is about satisfiability, right? Okay, I give this language which has say, let's assume propositional logic, and then I say, okay, whether this particular proposition is valid or not. So there is a whole tradition, right? This is like a 40-year-old tradition where they've invented techniques for automatically proving whether this particular question is valid or not. And for propositional logic without quantifiers, right? If you don't consider first order logic, this is very easy. In fact, this is a decidable question. So you can write an algorithm which will always give you an answer to whether a particular proposition is valid or invalid. Okay, but but if you sort of lift this level up and introduce, say, quantifiers, first order logic quantifiers, where you introduce for all and there exists, you lose decidability. So when you ask a question saying, okay, here is a statement in first order logic, is the statement valid? You can only these tools will sometimes tell you, okay, these statements are valid. Sometimes tell you these statements are invalid, but they might also say, I don't know. I just timed out. This is an undecidable question. So I tried the various techniques. I can't give you an answer for whether this particular question that you asked me is valid or not, right? But there are lots and lots of heuristics that have been described in the last 10 years, so that even for undecidable questions, right, full first order logic is undecidable. Even for this undecidable fragment, these tools, these SMT solvers, satisfiability modulo theory, which is essentially SAT solvers plus some theories, are able to give you answers. They become very, very rich. So they can reason about strings, they can reason about integers, complex integers, right? We've sort of looked at, oh, you have to use ring tactic here, you have to use linear arithmetic here. We have very rich integer theories which have been baked into these logics so that you don't have to ever think about what tactic to use. They will automatically give you this. You can reason about bit strings. You can reason about very complicated logics, sets, and what else is there? I think that mostly covers. You can encode a lot of these questions into this, right? There have been so much advancement in that SMT solver that we have interesting languages that have been built on this power of SMT solvers. And there is a language called Daphne, which is also from Microsoft Research, right? And there is Frama C, which is a verifier for the C language, right? And there is Y3, which is another tool which has a rich tradition, which can do C and OCaml and other things. Liquid types is an ongoing research project for Haskell. So essentially, you can write Haskell programs and then write rich specifications, which will be automatically verified by the SMT solver underneath. So these sit on the other side. Okay, so these are automated program verifiers, and as it is mentioned here, right? So on the left hand side, what you have is very expressive higher order logics. You have interactive theorem proving. So which is exactly what we did, right? We have this notion of tactics. We can like pick apart the proof and we can slowly build up the proof. On the right hand side, we actually have effectful programming. So we can have side effects also in our programs. We have SMT based automation. You can just ask a question about a program, it will automatically tell you something very nice. But we only have very weak logics in the sense that if you ask a very complicated question, as Vimala might tell you, it won't come back with an answer. It will just say, I just give up, right? But these look like two different camps, and both camps are like really nice. But the question is, can we bring them closer? There is this air gap that is sitting between these two camps, and F star is actually a language that aims to explicitly bridge these two camps. Okay, there is the interactive theorem proving, there is the automated verification, and F star tries to bridge the gaps. And what is F star? F star is just like a functional programming language with FX, right? In Coq, the core language, the Galena, is purely functional. There is no references, there is no arrays. You cannot do IO, you cannot do anything. But F star is like a full-fledged language, right? Where you can do, it's just like OCaml, Haskell, or F sharp. You can write real programs that interact with the real outside world, but also do references, heaps, and linked lists, and so on, right? It's very rich in that aspect. It has SMT-based verification. SMT is satisfiability modulo theory. It's like SAT solvers plus theories for advanced things like bit strings and integers. Doesn't matter if you don't know what this is, but we will see the power of these in F star using a lot of examples. This is not alone in this space. There are lots of languages like Daphne, Pharmacy, and Y3 in this space. F star is one other language here. Its core is based on dependent type theory, just like Coq. So where we were using this Curry-Hewitt correspondence in a very deep fashion, right? When we write theorems, they are basically types, and our proofs are basically programs that satisfies the types. We are going to use the same sort of reasoning in this area as well. And the key point, which we might not get to in F star, is that just like how we do interactive theorem proving in Coq, we can do interactive theorem proving in F star. So this is precisely bridging the gap that is here. This gap is being bridged by F star. Okay, so that is what we are going to see. And F star is a nice language to use even otherwise. Even if you don't use advanced techniques, it is quite nice. And you can take F star programs, right, and compile it down to F sharp or OCaml, or there is a compiler called Kremlin, where you can take a subset of F star called low star and compile it down to C. So the idea is that you will write your programs in F star, and you will actually extract very fast first order explicit memory managed C code. And the guarantee that you will have is that the C code does not have any bugs, right, which are due to memory management and so on, because you prove that those bugs do not exist with FStar. You can also directly compile it down to an assembly language. There is a subset of FStar called Whale DSL. We might not have time to see all of these, but FStar is rich enough to do that. And the main reason why FStar was invented is for this project called Project Everest from Microsoft, right? And and if you look at the state of internet security these days, right? When we look at HTTPS stack, the secure HTTPS stack, it is full of security holes. OpenSSL is what we use mostly today, and it's just rife with security holes because it is written in C. It's also very complicated code. So what this project Everest tries to do is that it tries to rebuild the entire internet infrastructure that is around HTTPS using FStar, extracting code that is as fast as or better than C code, right? That's the whole point of this FStar project. So it sort of comes backwards, right? So Microsoft Research is not in the business of building languages. They want to build Windows and provide products that are secure for their users. So that project is Project Everest. And as part of this project, they've implemented this language called FStar. Okay, so that's the history of this. There have been lots and lots of artifacts that have already come out of FStar. So my TLS is a verified implementation of TLS protocol, transport layer security, which is like the next version of OpenSSL, right? If you have SSL, then TLS is sort of the advanced version. So we have verified implementations there. We have verified parser generators, cryptographic libraries, verified assembly stubs that are necessary for very fast cryptographic libraries. And in fact, this code is in production these days, right? Not just within Microsoft. So Firefox has a crypto library that comes from this Project Everest. Windows uses WinQuick. Quick is also part of Chrome these days. This is a bit old now. Azure Cloud, right? If you use Azure Cloud, there is a verified Merkle tree implementation, which is all implemented in FStar. WireGuard VPN, this is like a really nice use case. WireGuard VPN is a VPN provider that is now embedded into the Linux kernel. So you can use, so this WireGuard is used to be a separate one when I made these slides. Now it's part of the Linux kernel. So Linux kernel uses parts of the artifacts that come from FStar project. Okay. And then it is also used in the Zinc crypto library for Linux. Tezos is a blockchain, and that blockchain uses products from FStar, right? So the impact is far and wide, right? So this is sort of how do I put it? So one of the prime movers in the space, right? And it's a tool that sort of benefits a lot of people without them knowing it, because as a Mozilla, as a Firefox user, I might not care about how these things are built, but in fact, at the core of these products that we use every day are these important pieces. Okay. Actually, I'll just stop here, and then we'll sort of look at code from next class. And it's going to be intro again, right? We are going to see small examples, and then we'll slowly build up to large programs, just like how we did Coq. But we'll move a bit faster because at this point, you know how to do a little bit of verification. So I'll stop here. Any questions on this so far?
Casey, you used the term effectful and effectless a couple of times. Could you go a little more into that? What does that mean?
It's effectful is basically good question. So the core language of Coq, right? When we write Coq programs, we cannot use references. We cannot use arrays, right? But if you look at real programs like OpenSSL or TLS, right? They're all reading buffers. They are manipulating buffers. Like these are arrays that they are modifying in place, right? So you cannot even describe those programs in the language of Coq. you have to use a separate language that you define within Coq in order to define semantics for it, which we'll read later. But these languages on the right hand side, you can define these semantics directly. In C, right? In C, you can write in place merge sort, right? Not in place quick sort, right? But you cannot describe that program itself in Coq because Coq doesn't have the notion of mutability. But in order to do real stuff like proving HTTPS stack and implementing really fast implementations of cryptographic protocols, you often need to manipulate arrays, and these are what are known as FX. So when you can't do read or write to mutable memory, then you cannot even prove those programs, right? And F star sort of fits in that area, and that is what I call as effectful programs. Does that answer your question, Shashan?
Yes, yes. So in a sense, I guess the effectful programs are that bucket of programs which can have a meaningful effect on the program state, so to speak, right? You can
Just
do
think
practical
about,
things with it.
yeah. Not, I mean, practical, impractical is different. Just think about references, right? We cannot manipulate heaps, right? We cannot modify a reference. We cannot implement arrays. You cannot modify a memory location. There are no notions of pointers, right? All of that is not part of purely functional world. And these are in order to even talk about these are known as effects. So if you modify memory, it is an effect. If you modify a pointer, it is an effect. If you write to say a socket, it is an effect. So these are all sort of things that are not mathematical in nature. So that is what we call as effectful programs.
So is there like a formal list of these parameters that quantifies effects, or is this just an informal idea?
Uh, a good question. So there is no formal definition, but anything that is the sort of it's a gray area. So you can sort of fold FX into purely functional world by using monads, right? So you can simulate the fact that you have state effect by using a monad. So I think you can't. It's very hard to formally describe it, but anything that can be simulated with a monad is an effect, right? So don't worry too much about this distinction right now, but we'll sort of see what those effects are as we go along.
This seems quite interesting. Thank you.
Okay, wonderful. Okay, I'll stop here and then we can catch up tomorrow. Thanks, everyone. Bye-bye.